Too quiet.
Morning. So in chapter 3, we basically try to use the derivative to understand the behavior of the function. Here, this is a function. We want to know the behavior of the function at x equal to 0. So it's a local, like how function works around x equal to 0. There are a couple of choices. We want to know at x equal to 0 is function increasing or decreasing. So you will find the first derivative and plug in 0 into the first derivative. If the first derivative is positive, it will be increasing. If the first derivative value is negative, that will be decreasing. See, the function is discontinuous. If you plug in 0, it causes a computation problem. Right now, if you plug in 0 for x, it will be 0 plus e to the 0, which is 0 plus 1, y equal 1. So there's no discontinuity of the function. So x equals 0 also is not a discontinuity. B is has a relative minimum. That is I think at the derivative would be equal to 0. So it looks like that we should calculate the derivative of the function and use that to make a judgment. Is it increasing? Is it decreasing? Or is it a relative minimum or maximum? Also, I guess if you have a grapher, you can graph the function to say at 0 what unit it is. But the algebraic way will be calculating the first derivative. Calculate the first derivative and plug in 0 to see if it's popular. Remember, the first derivative positive means increasing, first derivative negative means decreasing, first derivative equal to 0. Then you have to figure out if it's before or after. Is it a maximum or minimum? That's right. Or is it a plain point that's not one of them? Right. So the main focus will be we gotta have a derivative in order to decide the determine. So let's look at how we find the derivative. The function. To 2x plus power for differentiating x squared. When you're differentiating exponential function, you have to have itself as a factor, and then because of chain rule, you also have to find the derivative of the inside function. So derivative of the inside function, negative 2x has the derivative of negative 2. So negative 2 has to multiply e to the negative 2x. So negative 2 e to the negative 2. So remember, exponential function derivative itself, but then because of chain rule, you also have to differentiate the inside function and multiply that to it. That's our derivative. All right, to determine increasing, decreasing, we'll plug in 0, because we are identifying its behavior as x equals 0. So if we plug in 0, 2 times 0 is 0. So then the first term is 0. Second term is negative 2e to the negative 0. 2 times e to the negative 0, positive 0 is the same. Any number to the power of 0 is 1. So this is really 2. As we were saying, if the derivative is positive, then it's increasing. If the derivative negative, it's decreasing. Right now, this should be decreasing at x equals 0. Answer to the question should be decreasing because the derivative function is negative 2 when x equals 0. Could you put it on the desk? I don't know. Phone is different than the anyone else? Ethan? Carson? To calculate the derivative, plug in 0 into the derivative based on the negative. The calculation is as follows. Thank you. One is done. That should be everybody. So the answer should be decreasing because the derivative equal to negative 2. Do you have any homework questions? Yes. Number 9. They switched to a new version of Teams.
Okay.
So this is a graphic question. 3.5 is about curve sketching. So we already have the sketch of the graph, and so we're going from the other direction. So the first four questions, there's a function. We try to understand the graph. The other group of question, we have the graph. We try to understand the function. So we from the graph we can figure out what was the local maximum, local minimum. Those are the points you can find from the picture. This is a local maximum. That is also a local maximum because for a small intervals for x value. For small interval, this seems to be the highest point in the entire function. I mean, around that interval. So you can also pick a small interval. So this part will be the maximum value right there. So I think those are the only two I can find. This one, because it's empty, so we are not able to write or achieve that value. So I think there's only two local maximum. They are for the x value of 1, 2, 3. So the number 3, 4, 5, 6, 7, 8. So 3 and 8. So answer 3, 8. Local minimum. We did that was wrong.
Same graph. The other thing is that we
It says we have to get every answer right, but from the picture, I don't see any local maximum. So let's try to answer the rest of the question. The second question is a local minimum, like how many lower point left. So this is a local minimum because in this, for pick an interval around this point, you can see this point is lower than all the other neighbor points. And this, you can also pick this line. This is the lowest point. This point belongs to the graph. It's going to be this one and that one. That's the 2 and 5. So for the local minimum, we have 2 and 5. And then we're going to find the global maximum or the absolute maximum. We will picture, right? That is seem to be higher than that one. Among the two local maximum, this one is higher, but then there is a higher point at this point. Okay, so the entire graph, if you have to think of the single higher point, is over here. But that point is open, so we're not able to get there. I hope that can make sense. So in this picture, even though you kind of see a maximum there, because it's not it's unachievable, you don't have a local maximum. You can infinitely getting closer and closer to that spot. Since that spot is not allowed, we don't get there. I hope that makes sense. There's no actually. At point 3, it's here. So obviously this point is roughly like 0.2, 0.5, and then this may be 0.1, 0.001. It's higher than the 0.3. You cannot use 0.001 because there are 0.00001. So there is always points smaller than a given number. As long as we're not allowing x to be 0, that's empty, so x cannot equal 0. Maybe x equals 0 is undefined, maybe x equals 0 is something that we just can't get there. So the maximum seems to be there. We can see it, we just can't get to it. So I would say there's no maximum. If there's a solid point, we would have a maximum there. But this one, we would say none because the open interval. Basically, whenever there's an open interval, sometimes you get an asymptote. Sometimes it is a solve. It seems to be a point that it's achievable, but because it's the empty, we still don't get to use that point at the maximum. The minimum is, well, that is definitely the lowest point of the entire graph, and it is achievable. So we would see it's 5. Well, how do we answer use given graph question? Where does the function have local maximum? Where does it have local minimum? And this question is about what is the maximum. So you see none, and this says what is the minimum? It's at 5, but then the actual minimum value is a y value, so we should answer 2.
Yeah.
All right. So the first two questions is asking not the maximum or minimum, is asking for the location of the local maximum. It says where. That's why we answer the x value. But for the other two questions, we're actually asking the y value. And that's why I cannot answer 5 there, because 5 is the x value. So we'll have to answer the y value. I think that's what it should. It's a little bit picky because it's going to have all of them right to get credit. So as long as one of the answers wrong, you'll get a 0.
It's just nice.
Does that answer your question? Does that answer your question? All right. Other question. 7.
That's very good.
7.
Yes, one.
We might have to enlarge. The first question says, where does the function have an inflection point? It has this is a derivative. This is a derivative. So inflection point is when they contribute change. So inflection point is when the contribute change from positive to negative or negative to positive. And when does it contribute? So that will be the second derivative being positive or negative. So you have to, right at the inflection point, the second derivative is equal to 0. Now the second derivative is the derivative of the derivative. So it's really the derivative of the first derivative, so derivative of this one. So when this is a derivative, you're going to keep in mind the derivative function being positive, that's being increasing. That means the derivative of the derivative is positive. And then when the derivative is decreasing, that's the derivative of the derivative being negative. So positive second derivative, negative second derivative. So the inflection point is right in the middle because this is the derivative function, which is the points 0, -2, this must be -1. So the inflection point is -1. Any question? So when we are talking about increasing or decreasing of the derivative, we are actually talking about the second derivative. So this is the derivative function. Now this function, the whole derivative is all positive. See, that's the x-axis. So the entire derivative is positive, means the original function is increasing the whole time because this is all positive, so it's an increasing function. But the contributed change, because the derivative function goes from increasing to decreasing, right out there, that's when the contributed change. Make sense? Any questions for the first one? Given the picture, the first one will answer right there at that point. Where are the global maximum and minimum of the function? That's -2. This is +2. As we mentioned, right between the negative and +2, the derivatives. This is the derivative. The derivative is all positive, so the function is all increasing. So if the function has been increasing, it doesn't matter whether how it is increasing, but -2 and positive, it's been increasing. When we try to pretend this is the original function, that was a derivative the function. So because it's been increasing, at -2 you have a minimum, and +2 you have to have a maximum. So that's because the function is the increasing function, so minimum is x equals -2, maximum is at +2. All right, do you have the same picture from mine, or do you have a different picture? You have a different picture. All right, let me finish this one. Maybe I can look at yours. All right, so I'm gonna just try to explain. Maybe we have a variety of questions. We can try it. This question says if g of -2 equal to -1. Remember we were talking about at -2 there's a minimum. What are the possible values for g of 0? Right? We already mentioned that g of -2 is the minimum. This is say -1, and then what happened at 0? See, -2, 0, 2. -2 has to be higher than the -1, since -1 is supposed to be the minimum. So it has to be on the interval such as, it says enter your answer as an interval. So for example, you can enter this. Right. So we mean the value has to be higher than this number. So should be increasing. So it should be -1 should be the minimum to infinity. That means g of 0 is higher than -1. -1 is the minimum. And how is the value of g of 2 related to the value of g of 0? It is increasing, so it should be bigger than g of 0. As the x value increase, the y value should increase. That is all there is here. So I can try your version of it. Let me submit this one. Let's see. And I can also look at yours. You already finished. Okay, so you don't have to. We don't have to go through your version. Any other question? 3.5. Okay, it is a graphic question. We have 6 points. So we were looking at 6 spots on the graph. First one, we're trying to look for the greatest value, greatest y value. It happened at x2. So answer x2. Oh. Right. So it's the derivative. So you can see between x1 and x6, the entire function are positive. So then the original function is increasing, right? This is the x-axis. These are all on top. So it's increasing function. Then the highest point must be increasing to 1, 2, 3, 4, 5, 6. The last one is x6. So it must be highest at x6 and lowest at x1. We're just focusing on these 6 points. Explanation. It says at which of the marked value of x. So we only look at this marked value, the 6 number. Least one must be the smallest x value, being the smallest y value. Because the function is increasing. The derivative is greatest, right? Then the derivative's behavior, you can look at the graph. The derivative is the highest point. So we would go x2. And the derivative is least. We are comparing among the 6. 1, 2, 3, 4, 5. This is the lowest point. We don't compare with all the other values in the interval. When we compare the 6 of them, this is the lowest point. Given the 6 value, this is x4. So x4 is the lowest point. Let's look at second derivative. Remember, second derivative. This is a derivative. You can think of the derivative graph as the original, and the second derivative is a derivative of this graph. So when the derivative is greatest, the second derivative is a slope of the first derivative. So when you ask whether the second derivative is greatest, you're asking where is the slope of this graph greatest. So we're looking for the graph. This slope is 0, slope is negative, slope is 0, slope positive, negative. The greatest one is over here. So it seems like x1 seems to be the most steep of the graph. So answer x1. The least one should be a negative slope. So we look at this is negative, this is negative. I think that one's slightly less steep. So this is decreasing but pretty steep. It's increasing and steep. So I would answer x is 3 for the smallest segment. So this is a quite abstract function, since abstract question, because we don't know the actual formula of the function. So we are basically based on our conclusion based on the graph. Let's see. All right. For the sixth question, do you have any questions? Were you able to answer yours? Any other questions? So this will be the last question. All right. So today, let me start a little on 4.1. Like I said, chapter 4 can be called more application of the functions. Chapter 3 was already working on applying derivative to answer questions, and then in chapter 4 we work on more like the 5 questions that don't automatically give you the function formula. So I have to create the function formula. The first section, I think it's harder in some of the other sections in chapter 4. It's called related rates. Part of the reason is that it can be more abstract than other kind of problem. The topic is called related rates. So which really meaning that we're trying to study the relation between the rates. When you talk about rate, think about derivative. So you might be working on multiple derivatives. You're trying to find a relation between all those derivatives. And that's the thing. You may have multiple quantities that you have to study. And first you want to find out relation between those quantities. And then you're going to find the derivative of left side equation and right side equation. So it involves finding multiple derivatives. Let's try a question. All right, so this is what we was talking about when the quantities are related by equations. So set up a relation. And then the related rates is trying to find the relation between their rates. So instead of relation between the quantity, you're trying to find relation between their rates. And the way we determine the relation between the rates, we will be finding the derivative on either side of the equation. All right, let's look at the examples. So here we have a question. And so really depending on how familiar you are with that type of question, some of the related question is related to geometry. Some of the question is related to business, like how do you understand the relation between price and revenue. Okay, so this question is really a geometric question. It says the radius of a circle. Once you read the question, you start realizing how much do I know about a circle or a radius? What is the relation between the circle and the circumference? This question is about circumference. So as you are reading the question, you have to make yourself more familiar with the quantity in the question in order to write an equation that represents the quantity of the question. So we will see. I'm going to start using letters or variables to represent the quantity that is in the question. So as we were reading, radius for a circle is a quantity that kind of measures the size of the circle. So this is one thing. It's going at a rate of 5 inch per hour. This is something we want to keep in mind. Rate 5 minutes per hour. That is a rate. You can think of the rate there as a derivative. So you would say derivative of the radius is 5 inch per hour. Inch per hour, kind of think of it as a fractional unit. Because of fractional unit, this is actually comparable to speed. All right. Basically, the radius is growing. When the radius is getting bigger, the circle is getting bigger. The circle is getting bigger, the circumference is getting bigger as well. So we'll find out what rate is the circumference growing. So think about a circle, right? When the radius of the circle is increasing, of course the circumference is increasing. So another quantity in the question will be the circumference. We are trying to find the relation between circumference and radius. So as we were reading the question, we figure out what quantity are related. We have information for the rate of the radius, and the question is asking for the rate of the circumference. So having that in mind, first, normally with this kind of question, the first thing we'll do is to find out relation between the quantity. So first, write down quantity in the question. Right. Our number 1 is the radius. Number 2 is the circumference. Right. We don't have any other quantity. The rate of 5 inch per hour is related to the radius, rate of the circle, rate of the radius, and then we are asking for the rate of the circumference. So then, where's the quantity when you write the quantity in the question with a big name, the English word? So a little hard to put them in a formula. So instead, we're going to call them R and C. Now I'm just trying to make it easier to represent that the relation between them. Right now, this is a little background question. Do you know what's the relation between the radius and circumference? Or how do you calculate circumference if you have the radius? C equal to 2 pi times the radius, right? So that's the relation. Once you get the quantity, we need to know what is the relation between these quantities. So that should be an equation. So C equal to 2 pi times R. One of the ways we can figure it out is like this is the radius. So how many radius in the entire circumference? 1, 2, 3, 4, 5, roughly 6. A little bit bigger than 6. And that exactly is what this, right? Pi is 3.14, 2 times pi is 6.28. So there's a little bit more than 6 radius in each circumference. Radius 1, 2, 3, 4, 5, 6. So a little bit over 6 radius is in one circumference. The relation kind of makes sense. I mean, this is historically people find out the relation between the 2 times r is the diameter. In history, we actually look at the relation between the circumference and the diameter. Diameter is there's roughly 3 of the diameter is in one circumference. So that's the relation. But the question is not asking the relation, it's asking the relation between the rates. So we're gonna have to try to rely on the fractional notation for the rates. So the rates, we use the derivative notation. We'll say the rate of the radius, rates of the radius. We write that as d r dt. So the increasing of the radius is 5 inch per hour. 5 inch per hour. So the unit is indicating that the the time have a unit of hour, then the radius have a unit of inch. So this is how many inch per hour that the radius is increasing. So that is a speed, or you can call that is a derivative of the radius. Any questions so far? And then back to the question, it says at what rate is the circumference growing? So because the radius is growing, the circumference is also a smaller radius, smaller circumference, bigger radius, bigger circumference. So circumference also is supposed to be growing. So the question is, we're going to be clear about what exactly are we supposed to answer is the derivative of the circumference. So we can write the dc dt. So what is the rate of increasing for circumference? As we're reading, notice that there's something extra that was added in here. That is time. The inch per hour. Inch is the unit for the radius. Hour is a unit for time. So even though we mentioned the quantity, the radius, circumference are actually a hidden unit or hidden variable. That is the time. Because things are changing, as things are changing, we model the change by how they changes through time. So time is another variable that normally are not mentioned in the question. We kind of have to see this unit or this quantity, this variable in the unit. So inch per hour, we realize hour, which is the time is also related. So what we're going to do is to try to find the relation between VRDT and DCDT. In the question, the only thing we do know is VRDT, and we're trying to find the DCDT. So we kind of have to find out this derivative. So that will give us another thing. Now we got to find the derivative. So we're going to take this equation, and we are going to find the derivative of the equation, both sides of the equation, with respect to variable t, with respect to time. So we would to verb, to action, we're finding the derivative of that equation, those sides of the with respect to the verb. So we're basing on this equation, and this is a part that's slightly harder because in the past we always were using the derivative of using the derivative with respect to x. So that's now actually looking at the time, because time is a persistent variable in about anything in the world. So if you differentiate the left side equation, it's going to be dc dt. You can also call that c prime. But dc dt will kind of show you the unit division of the unit. dc dt is a derivative of the left side of the equation. Now we're also going to differentiate the right side of the equation and realize that this number 2 times pi is a number. We do not differentiate a number because if you try to differentiate a number, the derivative of a number will be 0. So differentiate 2 pi does not help. So it doesn't really add any information. So we're calling this as a coefficient. This coefficient 2 pi will be maintained, and then all you have to do is differentiate the pi. So basically, if you have 5 times function f, then derivative 5f is 5 times f prime. So all you have to do is differentiate the variable function, and the numerical number will be considered something that you carry around and don't have to differentiate. So keep the 2 pi, then multiply by the RDT. I believe this is how the textbook is going about it. But in the past, sometimes I get lazy. I write this kind of thing. I'll use the prime notation, and then having c prime is equal to 2 pi, and then the derivative of r, which will just be r prime. So that's really another notation for it. You can write it this way or you can write it this way. Essentially, they actually mean the same thing. What this one does is making the derivative more visible, and also so it's what we have in the original notation. So if you want to go by this notation, you have to realize what is the r prime. The r prime if the dRdt really equal to 5 to have R equal to 5. Now we can see how we go about calculating it. We're trying to find the dCdt, or we're trying to find the C prime. All we have to do is to realize that equal to 5. Equal to 5. So the following calculation is, this is equal to 2 pi times 5. So final answer is 10 pi. And the unit will be inch per hour. Inch per 10 pi, which is 60.2 inch for every hour. That's how much increase it is unit time. That's the calculation of the rate of increasing of the circumference equal to 10 pi. Any question? All right. So this is what I'm talking about. If you have practiced similar type of question for the related rate, you might be able to understand the reasoning. But if it's a brand new question, then number one, understanding the relation between the quantity difficult. And sometimes if students are new to related rate, we didn't realize that the underlying variable or the independent variable is actually t. Another thing that causes confusion sometimes is we have multiple variables. We have c, we have r, we also have t. So it's way more than what we were doing earlier. So we kind of have to get used to this idea of having more than 2 variables in a single equation. This is our first example for a related rate. Any question? Let's see the examples. So this one, it looks like another geometric question. It says water stream out of the faucet at a rate of 2 inch cube per second. So inch cube, it looks like a volume unit for the volume. This is 3-dimensional. S is the initial letter for the letter second. That's representing the time. So that is a rate. You can also call that is a derivative with respect to t. Onto a flat surface at a constant rate. So that will be the constant rate that we're talking about. Forming a circular puddle that is 1/8 inch deep. At what rate is the area of the puddle growing? Number 2, at what rate is the radius of the circle growing? So let's look at how what kind of quantity in the question. So we didn't really see the word volume in the question, but it did have the unit inch cube. So that's volume per second. So it's 2 cube inch per second. That's the rate of change of the volume. And it's forming a circular puddle that's 1/8 inch deep. So that's the height of the puddle, which is a very small height. And the area of the puddle is circular, but the height, we're assuming the height of the puddle is constant as 1/8 inch deep. All right, so what was the question? The question number 1 is asking the rate of change of the area. The second question is asking the rate of change of the radius. So as we're going through this, we're realizing that we're trying to find a relation between all these quantities. The only known, well, there's not the only, there's 2 known quantities. One is volume, rate of the volume, and then one is the actual height of the puddle. Right, so I'm trying to make a 3-dimensional picture of the puddle. So water is getting to it. Okay, so the rate of the how much was it? It's 2 inch cubes per second. All right. Based on the height, the depth of the water is 1 inch, 1/8 inch, 1/8 inch in this part that is from here to here. It's 1/8, the depth of the water. The question is asking some questions about the radius and questions about the area. Because the unit, I believe volume will also be the question. So this is really the dV dt that we got. The root of the volume is 2 inch cubed per second. Because of per second thing, I know that 2 is not a volume, it is a derivative of the volume. So through this question, you have to keep in mind that the unit carry a lot of information. To kind of look at the unit, there's an inch for the depth of the water. So we obviously are using inch for any distance relation in the question. We're using second for the time relation in the question. All right, so let's try to look at the quantity question. Volume, we have area, we'll just use A for area, and then we also have radius. All right, we did try to find a relation of all these quantities in relation to time, to the positive possible relation there.
Here is what I found.
All right, so now figure out, try to list any quantity that was mentioned in the question, and then we try to find the relation. It looks like we have given information about volume, so we have to think about geometry. What is the relation between? This looks like a cylinder, so I would say it's a cylinder. Right, so what is the relation between the volume of a cylinder? So how to calculate, do you remember how to calculate volume of a cylinder? Have you heard of the base times height? And this is a same way. A cylinder, there are two bases, the top base and the bottom base. The bases are circular, so the base area is pi r squared, right? The circle has area of pi r squared. So base area times height will be the volume. So let me try to write that. Volume of the cylinder equal to pi r squared is a base area. Pi r squared is area of a circle. Area of a circle times the height. All right, and then you can also think of this as V is equal to area times area of the circle times the height. Any questions so far? All right, let's try to find the relation. Through all this question, we already realized that the height is being held constant. So in the cylinder, the height is height equal to 1/8. The depth of the water puddle, circular puddle, is 1/8. So in a formula, the H is 1/8. That's already. There are two questions. Let's try to finish number 1. Okay. So question 1 is, we already knew that the volume had a derivative of 2. So we know that dV dt equal to 2. All right, we're trying to find what is the rate of the area flowing. So we're trying to find VA dt. Or you can say, we know the V prime equal to 2. We're trying to find A prime. We want to be short, be concise, but so this is the question. So you can see underneath it, we are trying to find the relation between the derivative of the volume and the derivative of the area. So if you want to find relation between the two, Number one thing is you've got to find the relation between V and A, right? In order to find the relation between their derivative, you have to first find the relation between their original quantity. So the relation between V and A is what's necessary to answer the question over here. Volume is 3-dimension, area is 2-dimension, but the height is one other dimension. So basically the area times the height equal to the volume. 2-dimension measure times 1-dimensional measure is a 3-dimensional measure. This is a relation between V and A. We already know that H equal to 1/8, so that is a direct relation which goes V equal to 1/8 times A. That's the relation between V and A. But that doesn't really answer the question because we don't know what is the V, what was A, but we know the derivative of V. So if you have derivative V, to find derivative of A, rate of V, rate of A, you're gonna have to find the relation between them. So we got a create equation that tells us dA dt. So we decided we're gonna find the derivative of the left side of this equation and also derivative of the right side of the equation. Again, the differentiation part, the derivative of the left side is a direct derivative of the quantity V. So derivative of the left side will just be the V prime or dV dt. dV dt or V prime is the same. But now I'm trying to expressively write the variable, right, the notation. Right, the right side, the coefficient 1/8 has 0 derivatives, so we don't differentiate since it's got 0. So we're going to keep that one. We're going to differentiate the A, which is dA dt. So as a consequence, if you differentiate left side and right side, you have 1/8 times dA dt. The derivative of A. So now we have this equation. This equation connected the derivative V with the derivative A. We know the derivative V equal to 2. So we know this side is 2. So in order to find the dA dt, which is really what the first question was asking, we'll plug in 2 for the dV dt. So we have the 2 is equal to 1/8 dA dt. Think of the dA dt as a single thing that we're trying to find. So don't have to think about it as the division. That's not a division, that's just a notation. If writing as a division notation confuses you, you can rewrite it as A prime. It really is 2 equal to 1/8 times A prime. Now we're trying to calculate the A prime, dA dt, A prime, same thing. So in order to get it by itself, we want to get rid of the 1/8. How do you get rid of the 1/8? Right? Oh, you can also multiply the reciprocal, right? Divide the 1/8, divide 1/8, and divide 1/8, and those are the equation. That's the same as multiplying the 8. So time 8 on the right, and we also time 8 on the left. That's going to be 16 is on the left, and then the right side will just be dA. And that finished the question. It's giving us a quantity for dA dt. To answer the question, the derivative of A, the rate of the area, is equal to 16. So the rate of the area of the puddle is growing at a rate of 16 inches square per second. The one-dimensional measure is in inch, two-dimension is inch square, three-dimension is inch cube. So using inch for the distance measure. This answers the first question. Any questions? It is similar to the implicit differentiation, but in the implicit differentiation we have x and y. We don't have a t, and so there's a less variable involved. But normally in this kind of question, we have to become more and more familiar with the background of the question. If this one is about geometry, so you kind of have to review what is a volume formula for cylinder. If you search up the volume for a cylinder, is this V equal to pi r squared times H. In the question, it did mention area of the puddle, so area of the puddle is really the pi r squared. So volume equals area times the height, or volume to pi r squared times the height. These are the two relations. This equation connected the volume with the radius. This equation, the V equal to A times H, connected the volume with the area. That's why I'm using this for question 1. Any question? So answer to the first question will be 16. Actually is 16-inch square per second. Since it's a rate, so the unit gonna be a division. Let's answer the second question. Answer question 2. Right. For question 2, we already have the, let me just call that V prime. We already have that the derivative of V equal to this equal to 2-inch cube per second. And the question is asking what is the rate of the radius? So we're asking what is a derivative R. The radius, that was the question. So if you want to find out, we have the V prime, try to find R prime. That is, you gotta first connect the volume with the radius. This is formula really goes out, so we will use that one. How the V is equal to pi r squared. How we have R in the same equation. The H equal to 1/8, so we go pi r squared times 1/8. Or you can just write 1/8 times pi multiplied by r squared. That is a connection. That's a connection. This equation connects the two quantities. The quantity are volume and radius. So what we're going to do is we are going to find derivative of the left side and derivative of the right side with respect to t. So if you find the derivative of the left side, it's v prime. If you find the derivative of the right side, it's going to be 1/8 times pi, which is just a number. And this is really something related to implicit differentiation. R is not a constant number. It is a function. It changes through time. So the derivative of this is 2r times r prime. And that's something similar to implicit differentiation, 2r times r prime. The reason for this is R is a variable, a function of time. So if you try to find the derivative power 2 of a function, then the derivative of this function, apply power rule, then you apply chain. So that's where we have R prime there. I mean, if you forget to add that part, you'll be wondering, I'm trying to find R prime. Where is that R prime? So R prime coming right out here when you are differentiating the R squared. Applying chain rule, it is equal to root of r squared is 2r times r prime. You can also write 2r times dr dt, but to make it short, I'm moving the prime notation here. Any question? So we're trying to find out what is the r prime in the question. Now we're going to plug in any information we already knew. We have the r prime equal to 2. And we're trying to find the r prime, but what is r is a question. It's 2r times r prime. I think it will have to carry the R in there. So this will be the answer to the question. We plug in the 2 for the R prime. And we'll have 2 is equal to 1/8 pi times 2R. We don't have a rate question. No. Rate question. We really don't have the R, so times the R prime. So if you want to calculate the R prime, That's the quantity we're calculating. So all the other quantity will be combined and divide out to the other side of the equation. So R prime is equal to, we end up having a formula, single quantity. So numerator is 2, denominator is 1/8 times 2R. So we'll cancel the common factor 2. Bring that the 8 is the denominator, so that brings up 8 to the numerator. So then the R prime is equal to 8/5 times R. Right, so that's the rate of the radius growing. Any question? All right, I don't have volume and I don't have area, so that's making it impossible to calculate the exact value of R at the moment. So we'll keep the answer that way. The answer is a little bit undecided because we're missing that number for R. So far, that's all we have. Any questions? So this is one of the related rate questions. So it does involve certain amount of knowledge of the background, such as volume, radius, and area. This kind of information can be reviewed, or you can also search the formula for it. So a single formula will be all that it takes to find a relation. Let's see. I have another example to review. So you see, we have the geometry question. There are other questions such as, right, so this is a question really about rectangle geometry. So you have a rectangle's area is being calculated by, well, this is about the parameter. Parameter of the rectangle equal to 2 times the length plus 2 times the weight. So that's the main relation. Geometry. Parameter is L plus L plus W plus W, so 2L, 2W. So the second question was area, relation between area. So area to the left hand weight for a rectangle. So then you can find derivative left side and right side. A little application of product rule there. Another example, right triangle. So a right triangle has, depending on what you are trying to find out, you might want to find the relation between the area equal to base times height. So area of the rectangle equal to 1/2 the base, which is x, times the height, which is y. This is a right triangle. Now, you can also find the relation between their lengths. So in the right triangle, the length goes ABC, or x, y, z. So x squared plus y squared equals z squared. So that is allowing us to find the relation between the lengths of a right triangle. So depending on which question we're looking at, these are cylinder-related questions. 2 different examples on the cylinder question. The solution also is already here. So if you need more examples to familiar yourself with the scenario, those are the steps for how we work on a related rate question. And this is a ladder question, a very common example. You put a ladder against the wall, so the ladder is like this way. So the ladder and the wall and the ground is forming a right triangle. So there's a right triangle relation there. It will create an equation, and the ladder have a constant length. So length of the ladder in this question is 13. So x squared plus y squared equals 13 squared. Pythagorean theorem. So it allows us to find a relation between this distance and that distance. Other question. So to try this question on the homework, you'll get more realistic question. Let me see what I assigned. Our assignment. So I didn't post that file just so we would, if you feel like need a little bit of help, go through these examples to see, helps you get a better idea. And this is our assignments. Right, let's look at the first one. for the related rate in our questions. You can see there's a big variety of questions. Depending on what question is in there, very likely there are a couple of geometric questions. Like this one is a spherical snowball. Sphere is a surface that's a round surface. It's melting in such a way that its diameter is decreasing at a rate of 0.2. At what rate is the volume of the snowball decreasing when the diameter is 10 centimeter? So this is a question when we're trying to find the relation between the volume and diameter. So you can see the quantity mentioned in the question is diameter and volume. We want to find the rate of volume when we know the diameter has a rate of 0.2 and the diameter itself equals 10. So that's a little bit more friendly than the example we just did. The example that we did, we have the rate of the R. We're trying to find the rate of R, and we have the rate of volume and try to find the rate of R, but we don't have that R value. So missing a single number to reach our answer. But this question we have both. So we have rate of the diameter. We also have the actual diameter. So to find the rate of the volume, we would first find out the relation of the volume diameter, and then from there we're able to find the rate of the volume. So this is the first question in homework assignment. Okay. So finish this one, and then they will come back to it tomorrow with the other questions. If you want to try your version of it, maybe I should assign it first. Really change the dates. Try to make sure it's available on your side of it instead of just on my side. Last time. Right, so now you should be able to see it. The first assignment, right? Try it on your side and see if you get a different number or the same number. So when you look at the question, number one thing is realize, well, are we really talking about what kind of relation exists between those quantities? So if you were reading through the question, you realize we're talking about a sphere, and we are talking about the spherical snowball and the diameter and the rate of the volume. So another quantity is the volume there. And we also have unit, which goes 0.2 centimeter per minute. So that is giving us the distance unit. Unit for the distance is centimeter. Unit for the time is minutes. So we know how we measure time and how we measure the length. The length is measured by centimeter. So this is how I try to go about analyzing it. So we want to be clear that whatever quantity that was in the question, diameter, which we could use letter D. Another one is volume. And there's the hidden variable, which is time. Right, and then we get minute for time and centimeter for the diameter. Volume can be calculated using the diameter, so we don't have a unit for the volume. But you can almost imagine the volume for the centimeter cubed. So distance measure of the one dimension affected how you measure the three dimension. What else? Time. But let me write the volume. So first we want to write down the relation. Anybody know how to calculate volume of a sphere? The volume of a sphere.
Radius squared.
But pi r times radius squared. That is area.
Oh,
Pi r squared
it's
is
cubed.
right. R should be cubed. Yes. So because the volume is three-dimensional, so it's supposed to be cubed. That's for sure. R cubed. Since this is related to a sphere, we should definitely have pi. All measure of circular shape always has pi. Always it. And there's one more factor, which is 4/3. 4/3 times pi times r cubed. That is a volume formula. If you want to find a two-dimensional measure, if a sphere has surface, the surface of a sphere is 4 pi r squared. Interesting fact is derivative of the volume, which is three-dimensional, is the surface area, which is two-dimensional. So if you find the derivative of this, will be this coefficient. Derivative of r squared, r cubed is 3r squared. 3r squared. So the 3 will cancel this way. So you end up having 4 pi r squared. Surface area for, we don't need it right now. I'm just trying to review. Surface, this surface, right? Surface A is equal to 4 pi r squared. Well, I just find that interesting that the derivative of the volume end up being the surface area. And that's kind of true for a lot of other geometric figures. So right now, this question only has volume in here. We're a little bit over time. We want to find a relation between volume and diameter, so we have to change this a little. Volume equals 4/3 pi times r. We don't have an r, so r equals diameter divided by 2. So that's really the formula we're going to work with. All right. Will we have more time tomorrow? We'll finish this one. In the meantime, we already knew the equation, and that's the equation we're working on. I'll see you tomorrow. Thank you. But keep finishing up your chapter 3. Right? Any questions?
Yeah. You're very welcome. Once again, yeah.